Hi everybody, the floor function is defined to be the greatest integer less than or equal to the input argument. Now I'm just going to make one up that's related to this problem. Let's do 60 over 29. Now it's called the floor. In the old days it was called the greatest integer function because it returns the greatest integer that is less than the input, which is sort of confusing all by itself, but it does make sense. Now let's break this down a little bit. This is the same thing as 58 over 29 plus 2 over 29. Okay, so this fractional part just kind of vaporizes. All right, this part of it right here less. Okay, I won't write down the formal definition. There's no need to really, because I'm going to work this a slightly different way. But again, 58 over 29 is equal to 2. That's equal to 2. And so you just chop this off essentially. Okay, so it's called the floor function. That's what I'll call it. Now what I'm going to do is take an approach that's some people will probably find unacceptable, but most of the college algebra books that I've seen taught out of, you can actually define a function by its graph. Okay, plain and simple. You know, most people are used to seeing like y equals f of x, or perhaps a tabular form, you know. But the graph can be a function, sometimes in a piecewise fashion, sometimes in its totality. Now let's get busy seeing how we can use the graph only to solve this equation that says the floor of x over 29 is equal to the absolute value of x minus 88. Now both of these have very clearly well-known graphs, okay? That this is the distance function essentially, and then this is the floor function that we've just mentioned. So let's get busy trying to draw a picture of this and see if we can get this thing solved. I'm just going to draw the left-hand side of this, or quadrant 1 behavior here. Okay, now, so what I'm going to do here, and hopefully it'll make sense as we move along here, I'm going to put 29 here. Okay, and any number less than 29 returns a fraction less than 1. And so the smallest integer less than a number that's less than 1 is just 0. And so what I'm going to do, folks, is just, so this is what the floor function looks like from 0 to 29. Okay. Now once you get to 29, the floor of an integer is itself. And so what I'm going to do right here is just make this should be an open dot down here, and I won't try to make a big deal about that, but it is true. And then so the next multiple of 29 is of course 58. Okay, 58. Now the floor of any number, the floor of x over 29 when x is between 29 and 58 is of course 1. And so I'm going to do this. Okay, let's just talk about an example. Let's look at the number just to make sense of this point. Let's call this, what do you want to call this, 48? 48, 1 is a point on the graph of the floor function. Right, everybody? Okay. Now, again, if you put 48 up here, you get a number that is between 1 and 2, which means its floor is 1. Okay, let's go out to the next multiple. 3 times 29, or 29 plus 58 is 87. And so we can get 87 right here. Okay, and in a similar fashion, we'll count up to 2 here on the vertical axis. We get this behavior. Okay. All right, again, let me put the circle. Again, it's not super important, actually, you know. Okay. And then finally, let's just go one more just for safety, for caution's sake. Let's go to the next multiple of 29. 4 times 29 is 116, right? Or 29 plus 87 is 116. Okay, and then we're going to get all the way up to 3 here, right? And so let me label that 3. Okay, and again, let's see, did I do all this right? Yeah, we got it going on like this. Okay, so this is any number between 87. For example, if you put 100 in here, 100 is a number between 3 and 4, so it has a floor of 3 and all the numbers in this interval. Okay, now let's compare that to the easy to graph absolute value function. The absolute value function is 0 when x is equal to 88, so right here. Okay, and again, y'all it's further over actually if you want to try to maintain scaling, but you would get something that looks like this. And it's hard, the scale of the x-axis is much larger, but notice that these are going to be the only 2 intersection points because this function, the floor function, increases very slowly, okay? Whereas this guy here has a slope of 1, minus 1 over here. So you see we have these 2 intersection points, okay? Here and here. Let me get those labeled prominently. And again, I'm not trying to make, now we're going to let the equations make a little bit of sense right here. Okay, again, this is the graph of the absolute value function. And this point right here is 88, okay? 88 comma 0. Now, how in the world do you make this thing fly? Well, in order for right here, the graph of this coordinate right here, let me get to this stage right here. The y coordinate has to be 2, meaning the function value itself, right? Okay, so how are you going to get that to happen both for this and this? Okay, well, the floor function does not care. As long as you're a number between 58 and 87, you're going to have a floor of 2, so it'll take any number you want, but we specifically need 86 right here, right? So we can see right here that this would have to be 86. Okay, 86. And I hope that makes sense. You can kind of let the absolute value function dictate things because the floor function takes on the constant value of 2 for this range of 29 numbers here, 29 integers that is, okay? So far we have x equals to 86. And you guys, oops, let me erase that. That would be, this is just the solution set that I'm trying to draw here, folks. So we would have 86 is one element in the solution set. And again, this is the set of x values that satisfy the above equation. Okay, now let's check out. We can see that it intersects at 3 also. Okay, well, any number between 87 and 116 has a floor of 3, but only one number satisfies this absolute value condition, right? And so let me just point it out right up here. Okay, this point would be 91, comma 3. And you see that, let's just call the floor function forgiving, for lack of a better word, right? See, because again, if you substitute 91 into here, you get a number slightly bigger than 3, but it's definitely less than 4, so its floor is still 3, right? But you need to be a little bit more specific, if you will, for the absolute value. We need 91 minus 88, right? So what we have is 2 solutions, 91 and 86. Okay, those are the 2 solutions I got. And now, without drawing the graphs, you wouldn't quite know if you were done here. You'd be having to use the definitions of both functions and working with it via logical manipulations. Now, I've waved my hand slightly. There can be no more solutions to the left or the right because of the nature of the absolute value function. It grows much faster. It increases in both directions, if you will. It's actually decreasing on this side, but it decreases at the same rate it increases. So it's outgrowing it. Never would run into the floor function over here is going to end up being negative, and the floor function will continue to be positive over here, but it's the absolute value function has no way of catching up with it because it increases 29 times as fast, so to speak, based on this right here. The slope of this as just a linear function is 1/29th, right? So hopefully that's a convincing argument, folks. Those are the two solutions I got. I appealed ever so slightly to the definition, but and again, these functions, I didn't draw the entirety of these functions. I drew them in the relevant areas. So I'm not claiming to have graphed both functions over their entire domains, but I graphed them over the germane areas of the domain to find the only solutions. And again, 86 and 91 are the only two solutions. All right, good night.